Picture, for a moment, a wide grassland at the end of a long, hot day. The sun has dropped low, the air is dry. Somewhere along a fence line, a small fire is burning in the dry grass, sending up a thin grey ribbon of smoke. It is the kind of small fire that people have watched for thousands of years. Quiet, slow, almost gentle. Then something changes. The smoke begins to lean. It begins to bend. It begins to turn. And in the span of a few breaths, that small ordinary fire stands up and starts to spin. A slender column of flame rises from the ground, twisting on itself like a thin orange ribbon. It dances along the field. It hums, it leans, and then, almost as softly as it came, it falls apart, and there is only smoke again. Fire scientists call this a fire whirl. People who have seen them in person often call them something older, a flame devil, a spinning candle, a pillar of fire across every continent where things burn. The same shape appears again and again, a column, a twist, a slow rotation that seems for a moment almost alive. Tonight we are going to sit beside this old, strange shape and wonder about it together. Because here is the quiet truth at the center of this episode. We understand fire. We understand wind. We understand rotation. And yet, when fire and wind and rotation meet, they sometimes do things that the best minds in the world still cannot fully explain. Before we go further, the planet has a new, quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. So let us begin with scale. Imagine standing on a low rise, looking out across the broad surface of the Earth. Below you, a thin skin of air wraps the planet. Above you, the sky stretches up into pale blue distance. Between those two layers, almost all the weather we have ever known unfolds. Wind, rain, cloud, storm, and, in certain rare places, fire that learns to spin. A fire whirl can be very small. Some are no taller than a person, thin as a candle, lasting only seconds. Others tower hundreds of feet into the air, roaring like a freight train, lifting burning debris into the sky. The largest ones, the rare ones, the ones that walk across whole valleys, are sometimes called fire tornadoes. Scientists are careful with that word. They are not quite the same as the tornadoes that drop from thunderstorms. They are something stranger, something that the fire itself seems to make. And this is the heart of our question, the soft mystery that we will turn over slowly across the long hours ahead. Why do fires sometimes build their own weather? Why does one fire stay flat and low and well behaved, while another fire, in a place that looks almost the same, suddenly rises up, gathers the air, and begins to turn? What determines whether a fire stays a fire or becomes a storm? The honest answer, the one fire researchers give in quiet rooms, is that we do not fully know. We have pieces, we have theories, we have computer models that get closer each year. But the precise recipe, the exact balance of fuel and wind and slope and heat that tips a fire into rotation, still slips through our hands. Some scientists believe terrain is the main key, the shape of a valley, the slope of a hill, the way air funnels through a notch in the land. Others suspect that the fuel matters more, the way dry grass burns differently from dry forest. Still, others point higher up, into the sky itself, where rising heat meets cool air and begins to twist. All of these ideas may be partly right. None of them, on their own, seems to be the whole answer. So this is what we will do tonight. We will not try to solve the mystery. We will not pretend it is solved. We will sit beside the question, the way people have sat beside fires, for as long as there have been people. We we'll look at the long, slow history of spinning flames. We will listen to the old stories and the new measurements. We will walk through marshes lit by pale lights and over hillsides that have burned for 1,000 years, and into laboratories where careful hands study how a single flame learns to turn. Settle in. Let your breathing slow. The fire is small and far away and warm, and the question, like the flame, is older than we are. To understand a spinning column of flame, it helps to first picture something gentler. Think of the steam rising from a hot cup of tea on a cold morning. The steam climbs upward because warm air is lighter than cool air. It rises in soft curling ribbons, sometimes drifting, sometimes twisting. Fire does the same thing, only with much more force. The flames heat the air above them, and that hot air shoots upward like an invisible chimney. Now imagine that rising chimney of hot air begins to spin. That, in the simplest terms, is a fire whirl. It is a tall, narrow tube of burning gas and superheated air that rotates around its own center, the way water rotates as it drains from a bathtub. Some are small and shy, others are tall and roaring. All of them share the same basic ingredients: heat, fuel, and a sideways nudge that turns rising air into spinning air. The smallest fire whirls are called fire devils. They are cousins to the dust devils you sometimes see crossing a hot field on a summer afternoon. A fire devil might stand only a few feet tall, no wider than your arm. It can flicker across a campfire, or dance briefly over burning leaves, and then fade in a second or two. If you have ever sat by a bonfire and seen a brief curl of flame lift off and pirouette, you have probably seen one without knowing its name. Larger fire whirls can climb 50 feet, 100 feet, sometimes higher. They look like slender orange ropes stretched between the ground and the sky. The very largest events, the ones scientists sometimes call fire tornadoes, can rise hundreds of feet and last for many minutes. A few rare ones in recorded history have reached heights that compare to a tall office tower, with bases as wide as a small house. These are extreme and unusual. Most fire whirls live brief lives and stay small. The temperature inside one of these spinning columns is hard to picture because it lies far outside everyday experience. A common wood fire burns at around 600 to 900 degrees Celsius. That is hot enough to soften glass. Inside, a strong fire whirl. The rotation pulls fresh air and fresh fuel into the core, and temperatures can climb higher still. The flames burn cleaner and brighter when the mixing is just right. In the very rare case of a so-called blue fire whirl, the column glows a soft blue rather than orange, because the fuel is burning almost completely. Scientists first watched one of these blue whirls form in a laboratory only about a decade ago, and they are still working out exactly why it appears. The composition of a fire whirl is the same as any flame. It is a mix of glowing gases, tiny soot particles, water vapor, and unburned bits of fuel. What makes the world different is not what it is made of, but how it moves. The spin gathers everything into a tight column. The flames lean inward. The hot air races upward through the center, and the surrounding air rushes in at the base to replace what has lifted away. This inward rush feeds the fire more oxygen, which makes it burn hotter, which makes the column climb faster. A small loop of self-feeding behavior begins. The conditions needed are surprisingly common, yet the result is surprisingly rare. You need a fire, of course. You need rising heat, and you need some source of rotation in the surrounding air. That rotation can come from wind curling around a hill, from two breezes meeting at an angle, from the way a valley funnels moving air, or even from the heat of the fire itself, reshaping the air around it. Most fires never spin. A few do. The exact tipping point between a still fire and a spinning one is still not fully understood, even by people who study fire for a living. Fire whirls have been observed in many settings. They appear in wildfires racing across dry forests. They appear in grassland, burns, and in farmers' fields. They appear in industrial fires, in oil fires, and sometimes in the aftermath of large explosions. They have been seen over burning peat bogs and over slow smoldering coal seams. Each setting offers slightly different fuel, different terrain, different weather. Each produces a slightly different kind of whirl. So the basics come down to this. A fire whirl is a rotating column of flame and hot gas. It can be tiny or towering. It is made of ordinary fire, shaped by a hidden twist in the air. And the question of exactly when one will form and how large it will grow remains an open puzzle to this day. Picture a small flame on the open ground. It burns quietly, sending a thin ribbon of smoke into the sky. The air around it warms and lifts. Cooler air slides in from the sides to take its place. This soft exchange of air is happening all the time, around every candle, every campfire, every burning leaf. It is the gentle beginning, the first whisper of what may, under the right conditions, grow into something far stranger. For a whirling flame to be born, that soft exchange must twist. The incoming air cannot arrive in a straight line. It must come in already turning, already carrying a hidden spin. This spin might come from the shape of the land. It might come from a passing breeze that curls around a ridge. It might come from two small currents of air meeting at slightly different angles. The flame itself does not create the spin. It only borrows it from the world around it. Once that spin enters the rising column of hot air, something quiet and beautiful begins. The column stretches upward, pulled by its own warmth. As it stretches, the spin tightens. Skaters know this well. When they pull their arms in close, they turn faster. The same simple law governs the rising air above a flame. The taller and thinner the column grows, the faster it rotates. A barely noticeable swirl at the base becomes a focused, humming whirl higher up. Fire scientists call this the stretching of vorticity. It is a long phrase for a soft idea. A weak rotation, when pulled and thinned, becomes a strong one. The fire itself provides the pulling. Heat rises, the column narrows, and the spin sharpens. If the conditions hold steady for long enough, a true fire whirl forms. A spinning sleeve of flame, sometimes only a hand's width across, sometimes wider than a house. The exact moment of birth is hard to catch. Researchers have filmed thousands of small fire whirls in controlled outdoor burns. They have watched them flicker into being and dissolve again in seconds. Yet the precise threshold remains slippery. One theory holds that a fire whirl forms when the rising heat is strong enough and the background rotation is just present enough to be captured. Another view suggests that the shape of the fire on the ground matters more than once believed. A long, thin line of flame, for example, seems to spawn whirls differently than a round patch of the same size. Which factor dominates is still being studied. The fuel beneath the flame also shapes its birth. Dry grass burns fast and light, sending up a quick hot plume. Heavy timber burns slow and deep, with a steadier draft. Pools of oil or fields of dry brush give different signatures again. Each kind of fuel changes how much heat rises, how fast, and for how long. A whirl that forms over grass may die in moments. A whirl that finds a deep, rich fuel bed may live for many minutes, drifting like a slow dancer across the burned ground. Terrain plays its quiet part as well. A flat plain offers little to deflect the incoming air, but a small hill, a dry ravine, a stand of trees, or even the wall of a building can bend the wind into curls. These curls feed the base of the fire with pre-spun air. In valleys and canyons, the effect grows stronger. The walls funnel the breeze. The slopes catch the rising heat. Fire whirls born in such places can be larger and longer lived than those born on open ground. Why some terrain features make whirls and others do not, even when they appear similar, remains an open question. Temperature differences across the fire matter too, where a hot patch sits next to a cooler one. Air rushes sideways before lifting. That sideways rush can roll into a horizontal tube of spinning air near the ground. If the fire then tips that tube upward, the horizontal spin becomes vertical. A whirl is born. Some researchers think this tipping mechanism explains the largest, most violent whirls. Others suspect the background rotation of the wider weather around the fire matters more. Both ideas may be partly right. So a whirling flame is not a single thing with a single origin. It is the meeting of many gentle ingredients. A little heat, a little spin, a little fuel, a little shape in the land. Each piece is ordinary on its own. Together, under the right quiet conditions, they conjure something that has fascinated and puzzled observers for as long as people have watched fire. How exactly the recipe comes together, and why it sometimes does and sometimes does not, is a question still being patiently asked. Long before any scientist tried to measure a flame, people watched fire move in ways they could not explain. They saw it rise, they saw it bend, and sometimes on rare and quiet evenings, they saw it spin. The oldest stories of our species are full of these moments. Tall columns of fire, glowing pillars in the desert, soft whirls of flame above the embers of a battlefield. We cannot test those old accounts in a lab, but we can listen to them, and we can ask what they may have been made of. To understand the ingredients of any flame, we have to go back further than memory. The carbon in a burning log was once part of the air. Plants pulled it from the sky over many seasons, breath by breath, and locked it inside their wood. When that wood burns, the carbon returns to the air as a gas. The fire is, in a quiet way, the slow undoing of sunlight. The light you see dancing in the flame is light a tree once stored, released again into the night. The oxygen feeding that flame has its own long story. Most of it comes from tiny ocean plants, small drifting cells called phytoplankton, that have been breathing oxygen into the sky for billions of years. Without them, no fire on earth would burn. A campfire in a forest, a candle on a table, a vast spinning column above a burning plain. All of them depend on the slow gift of microscopic life in the sea. Then there are the minerals. The ash left behind by any fire holds traces of the soil that fed the tree. Calcium, potassium, magnesium, tiny grains of iron. The iron is the strangest of all. Every atom of iron in that soft grey ash was once forged inside a dying star, long before our planet was born. When that star collapsed and scattered its insides across space, the iron drifted for ages. Some of it settled into the cloud of dust that became our world. Some sank deep to form the core, and some stayed near the surface where roots could find it. A fire whirl spinning above a dry field is in part made of starlight that traveled here across unimaginable time. The ancient accounts seem to sense this without knowing the chemistry. Many cultures describe pillars of fire as messengers, as guides, as something half belonging to the sky. In old desert traditions, travelers spoke of glowing columns that moved across the dunes at night. Some of these may have been dust devils, lit by distant lightning or by burning grass. Some may have been true fire whirls, fed by lingering brush fires. Some may have been nothing more than firelight, reflected in shifting air. We will never sort one report from another with certainty. The witnesses are long gone, and the flames left no trace. What we can say is that the conditions for a spinning column of flame have always existed on this planet. Dry grass, hot wind, the right shape of land, lightning to start a blaze, a long afternoon of heat to prepare the air. These ingredients were here 10,000 years ago, and 100,000 years before that. Early humans almost certainly saw fire whirls. They had no word for vortex, no theory of fluid motion, no understanding of how rising heat can twist a column of air into a spinning chimney. They only had the image, a tall, turning shape of light rising into the dark. Some researchers wonder whether certain sacred stories may carry the memory of real fire events. A pillar of flame in an old text could be a volcano seen from far away, its glowing ash column lit from within, or it could be a wildfire vortex on a grassland, witnessed once and remembered for generations. Other scholars argue that such stories are symbolic, not literal, and that we cannot map them onto any physical event at all. Both views remain open. The truth, if there is a single truth, has been softened by time. What stays across every account is the sense of awe. Spinning column of flame is made of carbon from the air, oxygen from the sea, minerals from the soil, and iron from a star that died before the sun was born. It rises for a few seconds, it turns, it vanishes, and whoever sees it tends to remember it for the rest of their life. We do not yet know which old stories describe real fire whirls and which describe something else entirely. The question sits quietly, unresolved, between history and physics. It is enough for now to notice that the ingredients of wonder have been with us for a very long time. To understand why a fire can grow into something far stranger than a fire, it helps to slow down and think about the quiet forces that shape it. Heat, pressure, gravity, and the soft pull of moving air all work together, even in the smallest candle flame. When a fire grows very large, those same forces grow with it, and sometimes, under the right conditions, they begin to sculpt the flame into something that behaves more like weather than like a simple burn. Heat is the first force. A flame is hotter than the air around it, sometimes by hundreds of degrees. Hot air is lighter than cool air, so it rises above a large fire. That rising air can climb very fast, faster than a person could run. As it lifts, cooler air rushes in from the sides to take its place. This inflow of air feeds the fire with fresh oxygen, and the fire grows hotter still. The cycle builds on itself, like a slow drum getting louder. Pressure plays a quieter part. The hot column above the fire is lighter than the air around it, so the pressure at the base of the fire drops. That gentle drop in pressure pulls more air inward from every direction. In a small campfire, you barely notice this. In a fire that covers many acres, the inrushing wind can knock down trees. Witnesses to very large fires often describe a strange, deep-breathing sound, as if the fire itself were inhaling. Gravity shapes the column from above. The rising plume of hot gas wants to climb, but gravity tugs at the cooler air around it. The boundary between the hot, rising cool and the cooler outside air becomes a kind of invisible wall. Along that wall, the air shears and folds, and tiny spins begin to form. Most of these spins die out. A few catch and grow. History remembers several fires where these forces aligned in terrible ways. In the summer of 1871, a vast fire swept through the forests around Peshtigo. In what is now Wisconsin, survivors spoke of a sound like a freight train, of trees lifted from the ground, of flames that seemed to leap from one place to another without crossing the space between. Whole towns vanished in a single night. The fire on that day burned with a fury that ordinary forest fires do not reach. Researchers still study it as one of the first well-documented firestorms in North America. Decades later, in 1923, a great earthquake struck the Kanto region of Japan. Stoves overturned in homes built closely together, and fires broke out across Tokyo and Yokohama. The flames merged into one enormous burn. In a place called the former Army Clothing Depot, a vast fire whirl is said to have formed in the open ground where many people had gathered for shelter. The exact size and shape of that vortex is still debated. What is not debated is that the fire that day taught a generation of scientists how a city of wood and paper could create its own weather. Other firestorms followed in other wars and other decades. In each case, observers reported the same haunting details. Day, roar like nothing else. A wind that pulled inward from miles away. Tall columns of flame rotating slowly, as if some invisible hand were stirring them. Ash carried high into the sky and then dropped, sometimes hours later, far from where the fire began. What makes one fire stay small and another grow into a self-feeding storm is still not fully understood. One idea is that fuel matters most. When the fire burns through dense, dry wood, it releases huge amounts of heat in a short time. Another idea is that terrain matters more, because valleys and slopes can funnel air in just the right way to start the rotation. A third view holds that the upper atmosphere is the hidden key. If the air high above the fire is unstable, the rising column can climb much farther and pull much harder at the surface below. Each idea has evidence in its favor. None of them, on its own, explains every case. Pressure, heat, gravity, and the shape of the land all push and pull on a large fire at once. They sculpt it in ways that are still being mapped, even with modern instruments. Fire scientists describe these events as humbling. The forces are simple, but the way they combine is not. Somewhere in that combination is the answer to why some fires become firestorms, while others, just as large, do not. For tonight it is enough to picture those quiet forces at work. The slow lift of warm air, the gentle pull of cool wind inward, the first faint stirring of a spin no one yet fully understands. A small candle flame stands about an inch tall. A campfire reaches the height of a sleeping dog. A house fire might climb to the height of a tree. These are the fires we know, the fires that fit inside our lives. They warm us, they cook for us, they can be measured by the height of a child. Now hold that image gently in your mind, because we are about to leave it behind. When a wildfire grows large enough, it stops behaving like a fire and begins behaving like a storm. The flames may rise hundreds of feet into the air. The hot gas above the flames rises much higher still. On the most extreme days, the column of hot air, pushed up by a single wildfire, can reach the very top of the lower atmosphere, roughly 7 to 9 miles above the ground. That is taller than the highest mountain on Earth. A passenger jet At cruising height would be flying through the upper smoke of such a fire. To feel that scale, picture a cooking pot on a stove. Imagine the soft ribbon of steam rising from it, reaching maybe a foot before it fades. Now imagine that same ribbon stretched until it pierced the clouds. That is the leap from kitchen fire to wildfire convection. The forces are not new. The scale is simply enormous. The heat output of a large wildfire is hard to picture in ordinary terms. A single tree, fully burning, can release as much energy per second as a small house furnace running flat out for an hour. Multiply that by the millions of trees in a fire's path, and the numbers stop being numbers. Some large fires release energy at a rate comparable to the steady output of a small nuclear power plant, and they do this for days. A few of the largest fires on record have released, over their lifetimes, more energy than some of the most powerful storms ever measured. That energy has to go somewhere. Most of it rises. Hot air is lighter than cool air. So a wildfire shoves a vast invisible column upward through the sky. This rising column is called a pyroconvective plume, which is just a fancy name for a tall stack of hot air pushed up by burning ground. As the air climbs, it cools. Any moisture it carries, from the trees, from the soil, from the fire itself, begins to gather into droplets. A cloud forms. A cloud born from fire is called a pyrocumulus. On the worst days, that cloud grows tall enough to become a thunderstorm, and we call it a pyrocumulonimbus. From the outside, it looks like any towering summer storm cloud, white and grey and shaped like a cauliflower, but its base is not made of ordinary warm air. Its base is fire. These fire-made thunderstorms can produce lightning. The lightning can strike miles ahead of the burning ground and start fresh fires in untouched forest. So the fire, in a sense, plants its own children far from itself. They can also produce strong downdrafts, sudden gusts of cold air that fall from the cloud and shove the flames in new directions. A wildfire, under a pyrocumulonimbus, can race forward at the speed of a galloping horse, then turn sideways within minutes, for reasons that even careful study has not fully explained. The footprint of one of these systems can be the size of a small country. The smoke can be lifted so high that it enters the upper atmosphere and drifts for months, circling the planet. Satellites have tracked smoke from single fires across entire oceans. A blaze in one forest can darken sunsets on the opposite side of the world. And yet the open question, the one that still puzzles fire scientists, is why some fires take this great leap and others do not. Two fires of similar size, in similar weather, on similar terrain, can behave in completely different ways. One smolders politely, the other births a storm. One theory points to small differences in fuel moisture, the dampness inside the trees themselves. Another points to the shape of the land, the way a slope or a valley funnels rising air. Third theory looks at the upper atmosphere, suggesting that what happens miles above the ground may matter more than what happens at the surface. None of these explanations, on its own, fits every case, so the scale is staggering and the rules are unfinished. A. Wildfire can grow tall enough to brush the edge of the sky, hot enough to make its own lightning, wide enough to be seen from orbit, and still, somewhere inside that vast cathedral of heat and smoke, the question of why it became a storm at all remains gently, patiently open. Imagine, for a moment, that you are floating high above a great forest in late summer. The trees stretch to the horizon in soft greens and dusty gulls. Smoke is rising from a single fire far below. From this height, the smoke does not look frightening. It looks slow. It looks almost peaceful. A pale grey column lifts itself from the canopy and climbs into the blue sky, growing wider the higher it goes. This is the surface of a wildfire seen from above, and it is one of the strangest sights on Earth. The base of the column is hidden in the trees down there. The fire is a bright orange line moving through the underbrush. Above that line, the air shimmers and bends. Heat warps the world. The smoke gathers itself into a soft, pale shaft that leans gently with the wind. Higher up, the column begins to spread. It opens like a slow, grey flower against the sky. If the fire is large enough, the column does not simply drift away. It grows. It pushes upward with surprising force. The hot air inside it rises faster than the air around it, and as it rises, it pulls fresh air in at the base. From above, you can see the smoke ring begin to curl. The column starts to take on a shape. It looks almost solid. It looks almost alive. The colors near the bottom are deep and varied. There is the bright copper of active flame. There is the dull red of glowing embers. There is the black of fresh char on bark and soil. Higher up, the smoke shifts through soft greys and browns. Near the top, where the column meets the cooler air far above the forest, the smoke turns a pale, milky white. Sometimes it spreads sideways into a flat anvil shape. Sometimes it climbs higher still, like a slow grey fountain. Within this column, fire scientists have long noticed something puzzling. The shaft of rising air is not always smooth. It can twist, it can knot, it can spin slowly around itself, like water draining from a deep pool. And every so often, a thin, bright thread of flame will detach from the main fire and rise inside that spinning column, climbing high above the trees in a thin orange line that almost no eye can quite believe. These are the tall flame columns that watchers from helicopters and lookout towers sometimes report. They appear and vanish quickly. They may be only a meter or two wide at the base, but they can stretch dozens of meters into the sky. The flame inside them looks stretched and clean. The air around them roars. And then, in a breath, they are gone. The column of smoke continues to rise, but the bright thread of fire has dissolved. Why these tall flame columns form, and why they last as long as they do, remains an open question. One idea is that they need just the right balance of fuel below and rotation above. The fire releases hot gases. The gases rise into a spinning column already formed by terrain or wind. The spin stretches the flame upward and protects it from being torn apart by side winds. Another idea is that the flame itself helps to organize the spin. The heat creates the lift creates the suction creates the rotation. In this view, the flame and the vortex make each other. Both ideas may be partly right. Fire scientists are still working out which conditions favor which behavior. They study photographs taken from above by aircraft and drones. They study heat signatures recorded from satellites. They study the slow, careful aftermath on the ground. And still, the tall flame columns over burning forests remain one of the harder things to predict. From above, the picture is quiet and almost beautiful. A green forest, a bright line of fire, a pale column rising in the late afternoon light, a thin orange thread that flickers once and is gone. The sun lowers. The shadows of the smoke stretch long across the treetops. The column blushes faintly pink near its base, catching the last warm light of the day. It is hard, looking down at such a scene, to remember how powerful these columns truly are. The soft grey shape that hangs above the forest can carry enough energy to bend the weather around it. The thin, bright threads inside it are small windows into something much larger and stranger. We can see the surface clearly enough. We can photograph it, measure it, watch it from a safe distance. But the question of why it behaves the way it does, on any given afternoon over any given forest, is one we have not yet fully answered. Beneath the loud, spinning columns of flame that tower over wildfires, there lies a quieter mystery. Not every strange fire roars. Some drift, some glide softly across the ground, low and pale, with no clear source feeding them. These are the quiet flames, the small wandering lights that people have reported for as long as anyone has kept records. They are far harder to study than fire whirls, and in many ways they are the deeper puzzle. Picture a damp field at dusk. The light is thin and blue. A soft flame, no bigger than a hand, hovers a short distance above the wet grass. It does not crackle. It does not burn the leaves beneath it. It simply moves slowly, as if carried by a breath of air that nobody can feel. After a few seconds, or sometimes a few minutes, it fades. No ash, no scorch mark, no fuel left behind, just the memory of a small pale light where there should have been nothing. Reports like these come from every part of the world, from the peat bogs of Ireland to the rice paddies of Japan, from the swamps of the American South to the cold valleys of Scandinavia. The names change. The descriptions are oddly similar. A soft glow, low to the ground. A flame without a candle. Sometimes the color is yellow, sometimes it is blue, sometimes it is a strange green that observers struggle to describe. For centuries, people explained these lights with folklore. They were said to be lanterns carried by spirits, or souls of the lost, or warnings from the land itself. The stories were beautiful, and they helped people share what they had seen. But the lights kept appearing long after the old stories began to fade, and so the question moved, slowly, from folklore into science. What is the source of these quiet, drifting flames, and why are they so hard to catch in the act? 1. Leading idea is that some of these lights are caused by gases rising from rotting plant matter in wet ground. Marshes and bogs hold deep layers of old leaves and roots. As these layers break down, they release methane and other gases. Under certain conditions, these gases may ignite at the surface, burning with a low, cool flame that hovers briefly before going out. This idea has support from chemistry, and small laboratory tests have shown that swamp gases can indeed light up under the right mix of air and spark. But this theory does not explain everything. Some witnesses describe lights that travel against the wind. Others describe flames that appear over dry ground, far from any bog, and many describe lights that linger far longer than a thin puff of methane should. So a second theory has emerged. Some researchers wonder whether certain glowing lights are not flames at all, but cold plasmas. Plasma is a kind of gas where the atoms have been split into charged pieces, and it can glow without burning. If small pockets of plasma can form near the ground during unusual electric weather, they might explain lights that drift without heat. The evidence for this idea is thin, and most fire scientists treat it with caution. A third possibility ties the lights to slow chemical reactions involving phosphorus compounds in the soil. Phosphorus can glow softly when exposed to air, and decaying bones or plant matter sometimes contain small amounts of it. But the glow from phosphorus is usually too faint and too still to match the moving lights people describe. So this idea too is incomplete. What makes these quiet flames so difficult to study is their shyness. They appear rarely, often alone, often at night, often in places where no instruments are watching, By the time a curious scientist arrives with a camera or a sensor, the light has already gone. There is no crater, no burn, no trail. The ground is sometimes a little damp, sometimes not. The air smells faintly of nothing in particular. There is almost nothing to measure, and so the question sits gently beneath the larger story of fire. Above the burning forests, we see giant whirling columns and rising thunderclouds of smoke. Below, in the quiet fields and old swamps, we see something far smaller and far stranger. A flame without a source, a light that drifts, a glow that does not consume what it touches. We do not yet know if these are one phenomenon or many. We do not yet know if they share a single cause, or if each tradition of sightings hides a different chemistry. They may turn out to be ordinary in the end. They may turn out to be something we have not yet named. For now, they remain among the softest mysteries of fire, drifting just out of reach. Some flames seem to follow their own slow rhythm. They come and go in cycles that have nothing to do with wind or weather. Old battlefields are one of the places where people have long claimed to see this. On certain quiet nights, in certain seasons, witnesses across centuries have described a soft glow drifting just above the grass. Not a roaring fire, not a steady lamp, something pale, low, and gently shifting. These reports come from many countries and many eras. Soldiers, farmers, travelers, and shepherds all left small notes in their journals. A faint blue light over a field where a battle once happened. A pale green flicker above a marshy hollow. A slow drift of luminous air, low to the ground, fading in and out across the hours before dawn. The accounts are calm rather than frightening. The lights do not chase anyone. They do not burn anyone. They simply move in soft, patient cycles, and then they are gone. What might cause such a glow has been debated for a very long time. One old idea is that bones and bodies, buried shallowly in the soil, release small amounts of a gas called phosphine. Phosphine can ignite in air at low temperatures, producing a faint, cool flame. In this theory, the slow breakdown of organic matter under the field provides a thin trickle of fuel. On damp nights when the air is still and the temperature is right, that fuel meets the air and glows. The cycle is seasonal: wet ground, mild nights, calm winds. When those conditions return, the lights return with them. A second theory points instead to swamp gas, which is mostly methane. Old battlefields were often fought across low ground, near rivers, marshes, and meadows that flood. The bodies of fallen horses and men, along with the churned earth itself, may have fed the soil with rotting plant and animal matter for years. Methane bubbles up from such ground in every season, and under the right conditions it can ignite or glow softly. In this view, the battlefield is not special because of what happened there. It is special because of where it sits, in the same low, wet places where marsh lights have always been reported. A third possibility takes the mystery in a different direction. Some researchers wonder whether many of these accounts are not flames at all. Cold light can come from living things. Certain fungi glow faintly in rotting wood. Certain bacteria glow in damp soil after a battle. The ground is disturbed, enriched, and shaded by new growth. A pale glow drifting above the grass might be a bloom of luminous microbes, pulsing through their own slow life cycle. The lights would still follow seasons, still favor wet years, still fade in dry ones. But the fuel would be life, not fire. Each of these ideas has strengths, and each has gaps. Phosphine is rare in nature, and hard to produce in the amounts the stories describe. Methane glows are real, but usually brief and small. Bioluminescent microbes exist, but few are bright enough to be seen across an open field. None of the theories alone explains every account. The truth, if there is a single truth, may be a quiet braid of all three, with different fields favoring different causes. What draws scientists back to these old reports is the rhythm of them. The glows tend to return on certain kinds of nights. Damp air, low wind, a temperature that hovers just above freezing in autumn, or just below warm in early summer. The cycles seem to match the slow breathing of the soil itself. The way it holds water, releases gas, warms, and cools through the year. Whatever the lights are, they appear to be tuned to that breathing. There is also a longer cycle, measured in decades, as old battlefields are ploughed, drained, built over, or simply forgotten. The reports fade. New fields, new disturbances, new wet hollows produce new lights elsewhere. The phenomenon, whatever its true source, seems to move with the slow turning of the land. It is not bound to any one place. It is bound to a set of conditions that the land sometimes offers and sometimes does not. This is where the soft glow above old battlefields fits into the wider mystery of unexplained fire. It is gentle rather than violent. It does not spin or roar, but it shares with the great fire whirls one strange quality. It chooses its moments. It follows a rhythm we can feel but cannot fully predict, and it reminds us that flame, in all its forms, is not only a thing that happens to the world. It is something the world seems to do, quietly on its own slow schedule. Step away from the burning forest for a little while. Walk down into the low country, where the ground turns soft and the air grows heavy with water. Here, on quiet nights, a different kind of flame is sometimes seen. It is small, it is pale, and it drifts above the wet ground like a lantern carried by no one at all. People have watched these lights for as long as people have lived near swamps, and though they are not fire whirls, they sit in the same family of half-understood flames that the earth produces on its own. In the old country names, these lights are called many things: will-o'-the-wisp, jack-o'-lantern, hinky-punk, ignis fatuus, which means foolish fire, because the lights seem to lead travelers astray. Each name carries the same story. A faint glow appears just above the marsh. It hovers. It moves softly when approached, and then, often, it fades. Whole villages used to swap accounts of these lights over their evening tea. Maps of bogs were drawn with little warnings about where they tended to appear. Scientists still do not fully agree on what causes them. One leading idea is that gases rising from rotting plants under the water can ignite when they meet the open air. Marshes are full of slow decay. Old leaves, old reeds, old wood all sink and break down without much oxygen. This produces methane, the same gas that warms our stoves, along with a few other compounds with longer names. One of these is phosphine. Phosphine has the unusual habit of catching fire on its own when it meets the air. If a small bubble of phosphine drifts up through the muck and ignites, it could, in theory, light a tiny pocket of methane along with it. That is one theory. There are others. Some researchers wonder if the cold glow of marsh lights might not be flame at all, but a slow chemical light, more like the soft shine of a firefly than the burn of a candle. Certain microbes in wet soil can release pale light through their own quiet reactions. Others have suggested that small electrical effects in the air above water, where mist and warm ground meet, might create faint, glowing patches without true combustion. The lights have rarely been captured cleanly on film, so it is hard to test any single idea well. What makes the question harder is that marsh lights, when they are seen, seem to behave a little oddly. Witnesses describe them moving against the wind. They describe them hovering at the height of a hand, then climbing slowly to the height of a shoulder. They describe a light that seems to retreat when you walk toward it, as if you were pushing a slow ball of mist in front of you. Some of this is surely tricks of the eye in the dark. A faint glow in the fog has no clear edge, and the brain fills in the rest. But not all of it is easy to explain that way. What ties these gentle lights to the larger story of unexplained fire is the same lesson told softly. The earth makes flame in many small, quiet ways. Some of those flames sit still. Some of them dance. Some of them spin into towering columns, and some of them barely lift above the reeds. They all draw on the same simple ingredients: fuel of some kind, oxygen of some kind, a spark of some kind. Yet the shapes they take are wildly different, and the rules that govern those shapes are still being worked out. The marsh and the wildfire are neighbors in this sense. They live in different rooms of the same house. The marsh light is fire at its smallest and shyest. The fire whirl is fire at its boldest and most spinning. Both depend on what the air is doing just above the ground. Both depend on slow chemistry beneath the surface. Both have been described for centuries with awe and a little confusion, and both still hold pieces that no laboratory has fully captured. Tonight, if you can, picture a low meadow at dusk, long grass bending under a soft mist, a single pale point of light, no brighter than a distant porch lamp floating above the wet ground. It does not roar, it does not threaten. It simply hovers, then drifts, then thins away into nothing. No one in the village can say with certainty what it was. They only know that it has been seen by their parents and their parents' parents in the same low places, in the same quiet weather. The marshes keep their lanterns, and the science of why they shine remains. For now, a gentle, open question, soft as fog. Among all the strange flames that drift across our world, perhaps none is stranger than the one that floats. For centuries, in the quiet aftermath of thunderstorms, people have described seeing small spheres of light moving slowly through the air. They glow like soft lanterns. They drift through windows, down chimneys, along the rafters of old barns. They linger for a few seconds, sometimes for a full minute, and then they vanish, often with a small pop, sometimes in silence. This is ball lightning, and after hundreds of years of careful observation, we still cannot fully explain what it is. The reports come from every part of the world, and from every century in which people kept written records. A sailor in the 18th century wrote of a glowing ball rolling along the deck of his ship. Farmers in quiet valleys described pale orbs passing through their kitchens after a storm. Pilots have seen them inside aircraft, gliding down the aisle without harming anyone, then dissolving into the air. The descriptions are remarkably consistent. The spheres are usually the size of an orange or a grapefruit. They glow yellow, orange, white, or sometimes a soft blue. They move slowly, against the wind as often as with it, and they seem to ignore the rules that ordinary fire follows. What makes ball lightning so extreme is its rarity. Most people will live their entire lives without seeing one. Scientists have rarely photographed them in the wild. Almost every piece of data we have comes from eyewitness accounts, which are precious but difficult to test. And yet the reports are too numerous and too similar across cultures to dismiss something real is happening. The question is what? One theory suggests that ball lightning is a kind of plasma, a hot ionized gas trapped inside an invisible shell of charged air. In this view, the lightning strike that triggers it leaves behind a small cloud of electrified particles, and these particles somehow hold themselves together for a few seconds before fading. A competing theory proposes something quite different. It suggests that when lightning strikes soil rich in silicon, it vaporizes tiny grains of the mineral. These grains rise into the air as a hot, glowing aerosol, slowly burning as they drift. The ball would then be a soft, floating ember of vaporized earth, not a plasma at all. Both ideas have supporters. Neither has been proven. In a laboratory in Brazil, researchers once produced small glowing spheres by sending strong electrical discharges through thin silicon wafers. The little orbs floated, glowed and lasted for several seconds before fading. They looked, by all accounts, very much like the ball lightning of folklore. But producing something that resembles a phenomenon is not the same as proving that it is the phenomenon. The spheres in the lab were small and brief. The ones seen in old farmhouses and on stormy seas have sometimes lasted far longer and moved in ways that no laboratory model has yet reproduced. The strangest reports describe behaviors that no current theory fully accounts for. Some witnesses say the spheres passed through solid glass without breaking it. Others say the orbs gave off no measurable heat, even when floating close to skin. A few accounts describe a faint hissing or crackling, while others report complete silence. The colors shift. The size shift. Sometimes the ball seems to follow a person across a room, as if drawn by something we have not yet measured. Each strange detail deepens the puzzle, and each new theory tries to account for a few of them while leaving others unexplained. There is, of course, the possibility that ball lightning is not one phenomenon, but several. Perhaps some glowing spheres are plasma, and others are burning silicon, and others still are something we have not yet imagined. The category may be a collection of different rare events that all happen to look alike to a frightened observer in a darkened room. Or perhaps there is a single hidden mechanism that ties them all together, and we simply have not found the right experiment to reveal it. What we can say is that ball lightning sits at the far edge of fire's strange behavior. It is the rarest of the rare. It is the flame that floats, the ember that drifts, the small bright thing that arrives without warning and leaves without trace. It belongs to the same family of mysteries as the fire whirl and the marsh light, all of them quiet reminders that combustion still hides corners we have not mapped. For tonight, it is enough to picture one of those soft glowing orbs drifting through a country kitchen long ago, watched by lamplight, remembered for generations, and still, even now, waiting patiently to be understood. On certain hillsides in the world, after the sun goes down, the rocks themselves seem to breathe out a soft blue light. The glow drifts low across the ground, pale and steady, like a sheet of cool water laid over warm stone. It pours from cracks in the earth. It pools in shallow basins. It curls up the sides of boulders before fading into the dark sky. To see it for the first time is to forget, for a moment, that fire is supposed to be orange. These quiet blue flames rise from sulfur. Deep beneath these hills, hot gases push up through the rock, carrying with them a yellow mineral called sulfur. When the gas meets the open air, and the air is warm enough, it begins to burn. The flame it makes is not the color we expect. It is a soft electric blue, sometimes almost violet, and it can stand many feet tall while making almost no sound at all. The best known place to watch this is a volcano in Indonesia called Kawah Ijen. There, miners walk through the night carrying baskets, and the blue flames rise around them in tall ribbons. The light is dim, dimmer than a candle, so it can only be seen properly after the sun has set. By day, the same vents look like ordinary cracks leaking pale smoke. The fire is there in the daylight too, but our eyes are too full of sunlight to notice it. Scientists who study these flames find a strange beauty in the small details. The blue color comes from the way sulfur burns. When sulfur gas meets oxygen at the right temperature, it gives off light in a narrow band that our eyes read as blue. Other fires give off many colors mixed together, which we see as orange or yellow. Sulfur fire is more pure. It glows in one quiet note instead of a chord. The flames also move differently than wood fires. They do not crackle. They do not throw sparks. They sway like slow grass underwater, bending with currents of air too gentle to feel on your skin. Sometimes they split into two thin tongues that wander apart and then rejoin. Sometimes they lie flat against the stone, hugging the ground, as if the fire itself were tired. A small mystery lives inside these flames. The blue light is not just from the sulfur gas burning in the air. Some of it comes from tiny droplets of melted sulfur, glowing as they fall back to the ground in slow yellow rain. Researchers have watched these droplets through special cameras. They form, they roll, they cool, and they harden into bright yellow crusts on the rocks below. The hill grows very slowly from its own breath. How tall can a sulfur flame become? On most days, the flames stand only a few feet high. But on rare nights at Kawa Aijen, the columns have been measured at more than 15 feet. No one is quite sure why some nights produce taller flames than others. One idea is that the gas pressure deep below changes with the weather, pushing more sulfur up when the air above grows cool and heavy. Another idea is that small shifts inside the volcano open and close hidden channels in the rock. The honest answer is that we do not yet know which factor matters most, or whether something else entirely is at work. There is also a question about how common these blue flames really are. For a long time, Kawa Aijen was thought to be the only place where they could be seen so clearly. Then quieter examples were found at other sulfur-rich volcanoes. In Ethiopia, in Iceland, in the high deserts of South America. Most are smaller, most are harder to reach. Each one glows in its own slow rhythm, and each one is shaped by the particular stones and gases beneath it. What makes scientists pause when they speak of these flames is the patience of them. A wildfire roars through a forest in minutes. A fire whirl spins itself out within an hour. But the blue flames of a sulfur hill can burn in the same crack for years, even decades. Fed by a slow leak from far below, they are fire without hurry. They are combustion, turned into a kind of weather, almost a kind of season. To stand beside one in the dark would be to feel very little heat at all. The flame is cool by fire standards. The light it casts on your hands would be blue. The rocks at your feet would shine faintly yellow, and the ground would smell faintly of struck matches, as if the planet had just thought of something and was about to whisper it to itself. Long before science had words for combustion, before anyone had drawn a flame diagram or studied the chemistry of gas, people had already noticed something strange. In certain quiet corners of the world, fires burned without ever going out. They did not need a campfire keeper. They did not need fresh wood. They simply burned, year after year, generation after generation, as if the earth itself were holding a candle. One of the oldest of these is the flame at Yanatas, on the slopes of a mountain in southern Turkey. Travelers there have described small fires drifting from cracks in the stone for more than 2,000 years. Ancient sailors said the lights helped guide them home at night. The Greeks wove the place into the story of a fire-breathing creature called the Chimera, and the name still clings to those rocks today. People knew the flames were real long before anyone could explain them. For most of human history, the explanation was simple. The fires were sacred. They were gifts or warnings or signs. Pilgrims walked great distances to sit beside them. Temples were built around them. In what is now Azerbaijan, a place called Yanar-Dag holds a wall of flame along a low hillside, and the country itself carries the old nickname of the Land of Fire. Worshippers of an ancient faith tended these flames as a quiet kind of prayer. They did not need to know the chemistry. The presence of the fire was enough. It took the slow growth of geology to begin asking different questions. By the 1700s, naturalists and traveling scholars were starting to write careful field notes about strange burning sites in Asia, the Middle East, and even Appalachia in North America. They sketched the rocks. They measured the heat. They noted how the flames bent in the wind, but never quite died. They began to suspect that something below the surface was rising up and feeding the fire from beneath. The first instruments were simple. A traveler might lower a candle into a crack to see if the air down there could catch. A scholar might collect the gas in a leather pouch and try to burn it later by a city lamp. These were rough experiments, often clumsy, sometimes dangerous, yet they hinted at the answer. The gas that fed these eternal flames was not magic. It was breath from deep inside the earth itself, slipping up through faults in the rock. By the 1800s, chemists could name what they were collecting: methane, a simple compound of carbon and hydrogen, light enough to drift upward, eager to burn the moment it met a spark. The fires at Yarnatus, at Yanar-Dag, and at small seeps around the world all seemed to share this common fuel. The mystery, it seemed, was solved. The earth was leaking gas, and lightning or human fire had lit it long ago, and the flame had simply never been allowed to die. The deeper question was harder. Where exactly was the gas coming from? How long would it last? Why did some seeps feed fires for centuries, while others gutted out in a single season? Researchers studying Yarnatus have suggested that the methane there may be created by an unusual chemical reaction between water and certain minerals deep underground, a process that could keep producing fuel for a very long time. Others wonder if the gas is older, trapped from ancient swamps and slow cooked over millions of years, and now simply leaking out through cracks made by old earthquakes. Both ideas have evidence behind them. Both leave gaps. The chemistry of these slow, eternal flames is still being measured, still being debated in quiet laboratories. The fires are not as showy as a wildfire vortex, or as violent as a fire-generated thunderstorm. They are patient. They have been patient for thousands of years, and in their patience, they hold clues about what the deep earth is doing beneath our feet. It is worth sitting for a moment with how strange this discovery really is. Humans walked past these flames for countless generations and felt only awe. Then, slowly, with cracked notebooks and candles and small glass jars, a handful of curious people began to ask what the fire actually was. The answers came in pieces, over centuries, and they are still arriving. Each new study of an eternal flame is one more small note in a long, slow conversation between people and the planet. Somewhere tonight, a quiet flicker is rising from a crack in old stone. It has been burning in one form or another since before any living person was born. No one is tending it. No one needs to. It simply keeps burning, soft and steady, while the cool dark settles around it. Beneath your feet, in places scattered across the world, something strange is happening. coal seams are burning, not in mines we have lit by accident, but in deep underground beds of ancient carbon that have been smouldering for years, for centuries, and in a few cases, for thousands of years. They burn slowly, with very little oxygen, deep in the dark, and the heat they release can rise to the surface in ways that surprise even the people who study them. This is one of the great surprises of fire on Earth. We tend to think of fire as a bright, fast, hungry thing. We picture flames leaping, smoke billowing, the crack of dry wood, but underground, fire wears a different face. It is patient. It is quiet. It can move through a coal seam at the pace of a slow walk per year, eating its way through buried fuel that has waited there since the age of the great fern forests, 300 million years ago. In parts of Australia, one such fire is thought to have been burning for around 6,000 years. It hides beneath a sandstone ridge called Burning Mountain in New South Wales. From above, the ground looks almost normal. There are patches of bare, pale soil where nothing grows. Faint wisps of vapor drift up from cracks in the rock. The stone, in some places, feels warm to the hand. Yet the actual flame is far below, perhaps 30 meters down, slowly consuming a thin layer of coal in near darkness. How a fire like this begins is itself an open question. One theory points to lightning, striking an exposed seam long ago and igniting the coal where it met the air. Another idea suggests spontaneous combustion, in which certain coals warm themselves slowly as they react with oxygen until the heat builds enough to ignite the seam from within. A third possibility is that ancient brush fires reached down through cracks and lit the carbon below. In most cases, no one can say for sure which spark did the work. Once such a fire is lit, the strangeness deepens. The flames need oxygen to burn, but oxygen has to travel down through narrow fractures in the rock. The smoke and heat have to travel back up through other fractures, so the burning seam becomes a kind of slow chimney, with cool air drawn in on one side and warm gas rising on the other. The fire can shift direction over decades as new cracks open and old ones collapse. It follows the coal the way a candle follows its wick, only across geological time. The temperatures involved can be surprising. Inside an active coal seam fire, the burning front can reach well over 1,000 degrees Celsius. Yet, at the surface, only a few meters above, the ground may feel merely warm, or steamy, or oddly bare. The rock acts as a thick blanket. Heat leaks out in faint plumes, in patches of melted minerals, in soils that have been baked into strange red and yellow clays. Geologists sometimes call this baked rock clinker, and it can be found in great red bands across the American West, marking ancient coal fires that burned out long before any human saw them. There is another counterintuitive detail. Some of these underground fires release flames at the surface that flicker and dance in ways that look almost alive, where a seam vents through a narrow crack. Escaping gases can ignite as they meet the open air. In the cold dark of a winter night, observers have described small blue and orange flames hovering at the lip of a fissure, lit from below, with no visible fuel. The fuel is real, of course. It is just buried. What surprises fire scientists most is how poorly we can predict the behavior of these slow fires. Coal seam fire may sleep for years, and suddenly accelerate when a roof collapses and lets in fresh air. It may follow a path no one expected, turning beneath highways, beneath towns, beneath forests. Efforts to put them out by pumping water, foam, or inert gas into the ground have sometimes worked and often failed. The fire simply finds another route. One researcher has compared the task to trying to extinguish a candle that hides itself inside a maze. How many of these fires are burning right now beneath the surface of the world is itself unknown. Estimates run into the thousands on every inhabited continent. Some are small, some span many kilometers. They release heat and gas into the atmosphere in quantities that are still being measured and argued over. The question of how long they have been burning and how long they will continue is one of the quietest mysteries fire has to offer. Among the strangest reports gathered by fire researchers are accounts of flames that begin to spin in air so still that not a leaf moves nearby. Witnesses describe a perfectly quiet meadow, a windless afternoon, the smoke from a small fire rising straight up like a grey rope. Then, with no warning and no breeze, the column begins to turn. The flame stretches taller. The smoke twists into a slow spiral, and the fire, which moments before was calm, starts to behave like something almost alive. These quiet air wells puzzle scientists because the simplest theories of fire rotation rely on wind. A breeze brushes past a hot column. The column tilts. Vorticity, which is the spin already present in moving air, gets squeezed and stretched into a tighter, faster rotation. That model works well for whirls born in gusty weather, but it does not explain the ones that rise in stillness when the surrounding air feels glassy and motionless to the people standing nearby. One possibility is that the air is not as still as it seems. The atmosphere near the ground is layered with thin sheets of air, moving at different speeds, even on calm days. The human skin cannot feel these soft layers, but a fire can. Heat lifts the lowest layer upward, and as it rises, it brushes past slower air above it. The shear between the layers may be invisible to us, yet strong enough, in theory, to start a slow rotation in the rising smoke. The whirl, in this view, is a quiet conversation between flame and atmosphere that we simply cannot sense with our own bodies. A competing idea points inward to the fire itself. Combustion is never perfectly even. Pockets of fuel burn hotter than others. Embers shift. A log collapses, opening a new vent for oxygen. Each of these small changes sends pulses of warm gas upward at slightly different speeds. Some researchers wonder whether the fire can essentially organize its own spin from these internal asymmetries, with no help from the wind at all. In that picture, the whirl is born from the chaos inside the flame, not from the air around it. Both theories may be partly right. Fire is a meeting place. It is chemistry, fluid motion, and weather all braided together in a single rising column. The way these systems connect mirrors the way other Earth systems behave. The sun warms the sea unevenly, and the sea answers with currents. A volcano breathes ash into the sky, and the sky responds with darker sunsets and cooler summers. A wildfire heats the lower atmosphere, and the atmosphere answers with its own clouds, its own rain, its own winds. A small flame on a calm day is the same story written in a smaller hand. Scientists studying these connections have begun to see fire as a node in a much larger network. The heat of burning wood lifts moisture out of the ground and the surrounding plants. That moisture climbs with the smoke and condenses high above the flame, forming the pale cap of a pyrocumulus cloud. Even a modest fire, in the right conditions, can pull a thread of weather into existence above itself. The whirl on the ground and the cloud overhead are part of the same slow exhale. What makes the windless whirls so interesting is that they hint at a quieter, more delicate version of this exchange. The fire is not shouting at the sky, it is whispering. And somewhere in that whisper, The conditions align just enough for rotation to begin. Researchers have tried to recreate the effect in laboratories, lighting small pools of fuel in sealed chambers with no fans, no drafts, no outside motion. Sometimes a whirl appears, sometimes it does not. The reasons remain difficult to pin down. Other Earth systems show the same stubbornness. Dust devils form on calm desert mornings without obvious cause. Water sometimes spirals down a drain in one direction, sometimes the other, regardless of the hemisphere. Slow rivers develop eddies along their banks, for reasons that depend on the smallest pebbles below the surface. The world is full of these small, self-organizing turns, and fire seems to belong to that family. For the listener, drifting towards sleep, it is enough to picture the scene: a still afternoon, a small fire in a clearing, smoke rising in a soft grey line, and then, without a breath of wind, the line begins to turn. No one knows exactly why it chose that moment. The flame and the air have agreed on something, in a language older than words, and we are still learning the shape of their quiet conversation. The mystery sits there, patient, in the warm light of the burning wood. For as long as people have lived near fire, they have told stories about it. And the stories rarely stay still. They shift from one century to the next, taking new shapes the way smoke takes new shapes in the wind. The folklore of spinning flames and dancing lights is one of the oldest threads in human memory. It runs through every continent, every climate, every long night beside a hearth. And the way these stories have changed across time may tell us almost as much about fire as the science does. In the dry grasslands of southern Africa, older traditions described whirling flame spirits that walked across the savanna after lightning storms. In parts of East Asia, foxfires and lantern ghosts drifted over rice fields at dusk, pale and silent. In northern Europe, will-o'-the-wisps led travelers astray through bogs and damp forests. In the Americas, certain people spoke of fire dancers who lived inside burning mountains. The details differ, the pattern repeats. Across cultures that never spoke to one another, fire is treated as something almost alive, something with its own will and its own quiet purpose. Listen closely to these stories, and you hear a careful observational mind at work. The wisps in the marsh tend to appear in the same wet, low places where decaying plants release flammable gases. The dancing lights over old battlefields appear where bones and organic matter slowly break down in the soil. The whirling flame spirits arrive after long droughts, in the season when fire whirls form most easily. The folklore is not random. It is shaped, slowly, by what people actually saw, generation after generation, in those specific places. What is interesting is how the stories have changed. Centuries ago, the explanations were spiritual. A fire whirl might be a messenger, a warning, a punishment, a blessing. The flame was a being. Then came the long shift toward natural philosophy, and the same lights were renamed: marsh gas, phosphine, static discharge, combustion of methane near the soil. The phenomena did not change, the framework did. And in the gap between the old language and the new, a great deal of careful detail was lost. Some folklorists wonder whether the older accounts preserved observations that modern science has yet to catch up with. There are stories of slow blue flames that hover at waist height in calm air. Stories of small flame spirits that follow a person down a path and vanish at a stream. Stories of pale fire that gathers in the same hollow every autumn. One view holds that these are simply embroidered tales, shaped by fear and firelight. Another view, gentler and more curious, suggests that some of these accounts describe real phenomena we have not yet measured. The truth may sit somewhere between and may move with each new study. The folklore itself keeps changing, even now. In the last 2 centuries, the stories have softened. The fire spirit became the swamp gas. The swamp gas became the curious blue flame. The curious blue flame became a footnote in a chemistry textbook. And then, in our own time, the stories have begun to shift again. Photographs and videos from large wildfires show vast spinning columns that look exactly like the old descriptions of fire dragons and flame serpents. The imagery has come full circle. Scientists studying these events sometimes reach, almost involuntarily, for the older language. Words like beast, like creature, like living thing. The folklore returns through the back door. There is a slow truth in all of this. Human understanding of fire is itself a kind of long, drifting flame. It flickers, it changes shape, it illuminates one corner of the mystery for a generation, then dims, then brightens somewhere else. The shepherd who watched a spinning column move across a dry field 3,000 years ago saw the same physics that a fire scientist sees today on a high-speed camera. They simply wrapped the observation in different words. Neither of them, perhaps, fully understood what they were watching. Some researchers now study folklore deliberately, sifting through old accounts of fire and light for patterns that might guide modern investigation. The bog lights of one region, the hill fires of another, the dancing flames reported in the same valley over 4 centuries. These records are imperfect, full of embellishment and faulty memory. Yet within them, sometimes a thread of careful observation glints. The question of what to trust and what to set aside remains open. The flame keeps dancing. The stories keep changing, and somewhere in the long conversation between the two, the slow shape of the mystery continues to turn, century by century, like a column of fire that no one has ever fully described. There is a particular kind of fire whirl that seems to defy what we expect from flame. It rises not over dry brush or scorched timber, but over water, over flooded fields, over the wet edges of marshland where the ground squelches underfoot. The light it casts is strange and soft, often more golden than orange, with a quiet shimmer along its base where the heat meets the damp. Reports of these waterborne flame columns are rare, but they appear scattered through the records of firefighters, sailors, and rural observers. A boat captain on a wide southern river describes a slow rotating pillar of fire drifting over the surface, fed by a layer of burning oil spilled from a nearby fuel barge. A farmer in a flooded paddy field watches a small spinning flame skip across the shallow water, lit by methane bubbling up from rotting plant matter beneath. In each case, the light behaves in a way that catches the eye. It glows, it pulses, it seems softer than ordinary fire, as if the moisture in the air has wrapped itself around the column like a thin veil. Light tells the story here in a way that nothing else can. Dry fire whirls usually burn with that sharp, hungry orange we know from campfires and brush fires. The flame is fed by solid fuel, and the carbon particles inside glow yellow and red as they heat. Over water or wet ground, the fuel is often different. It may be a thin film of oil. It may be marsh gas rising from the mud. It may be vapor from a tank breach drifting low across a lake. These lighter fuels burn cleaner, and they often give off a paler, gentler light. Some witnesses describe it as the color of old brass. Others say it looks almost translucent, as if you could see through the flame to the dark water beyond. The mystery is not only the color, but the persistence. A spinning column of flame over wet ground should, in theory, struggle to survive. Water cools the air around it. Damp surfaces resist ignition, yet there are credible reports of these vortices holding their shape for several minutes, slowly drifting along the surface, leaving a faint trail of steam behind them. One idea is that the rising heat from the burning fuel pulls in moist air at the base, and that this moist air, once heated, becomes part of the rotating column itself. The water vapor inside may scatter the light from within, producing the soft, almost lantern-like glow. Another idea points to the smoothness of the surface. Water is flatter than any forest floor. Wet mud is flatter than any hillside. A flame whirl needs a steady inflow of air to keep spinning, and a flat surface lets that inflow arrive evenly from all sides. On rough ground, eddies break up the rotation. On still water, the rotation may hold together longer than anyone would expect. Whether this is the main reason these vortices persist, or only a small part of the puzzle, remains an open question among fire scientists. The blue fire whirl belongs in this conversation too. In a small laboratory experiment some years ago, researchers placed a pool of liquid fuel inside a quartz cylinder above a tray of water. A normal yellow fire whirl formed at first, but then something unexpected happened. The flame shrank, calmed, and turned a clear, cool blue. The soot vanished. The light became almost ghostly. The team suggested that the blue whirl burned its fuel completely, leaving nothing behind to glow yellow. Other researchers have wondered whether the effect depends on very specific conditions that are hard to reproduce outside the lab. The question of whether such blue whirls ever form naturally over open water remains unsettled. What these wet ground flames share is a quality of light that feels out of place. Fire is supposed to be loud and bright. These columns are quiet and dim. They flicker like candles inside frosted glass. They cast pale reflections on the water around them, doubling the image into something that looks like two flames touching tip to tip. Sailors in old logbooks sometimes confused them with other lights at sea. Marsh travelers confused them with lanterns. The line between burning fuel, glowing gas, and trick of the eye can be very thin in low light over still water. Why some flames over wet places glow gold, why others briefly turn blue, why a few spin at all when the surface beneath them refuses to burn. These questions sit unresolved in the quiet corner of fire science. The light is real, the witnesses are sober. The full explanation has not yet arrived. Sound is something the fire world does not let you forget. Witnesses who have stood near one at a safe distance tend to describe the same thing first. Not the heat, not the color, the roar. A low, sustained, layered roar that seems to come from everywhere at once, the way a heavy rainstorm sounds when it surrounds a small house at night. The flame itself does not really sing. It is the air around it that gives the fire its voice. That voice has several parts. The lowest layer is a deep rumble, often described as freight train-like, the same comparison people reach for when they try to describe a tornado. The middle layer is a rushing, breathy hiss, the sound of millions of cubic feet of air being pulled upward and inward into the column. The top layer is sharper. It is the popping and snapping of fuel, small branches bursting, sap boiling, pockets of moisture turning to steam inside wood. Together these layers blend into something steady and almost musical, in the way that a long ocean wave is musical. The deep rumble is the most mysterious part. Fire researchers have long wondered exactly what produces it. One idea is that the roar comes from the rapid expansion of heated air, each tiny burst overlapping the next until the bursts blur into a continuous tone. Another idea is that large fires generate slow, low-frequency pressure waves, infrasound, sound too low for human ears to hear directly, and that what we feel as a rumble in the chest is partly this hidden bass note, bleeding into the lower edge of hearing. Both ideas may be partly right. The question of how much of a Fire Whirl's sound is infrasound and how much is ordinary noise is still being studied. Infrasound is interesting because it travels very far. A large fire-generated storm can send pressure waves through the atmosphere for hundreds of miles. Sensitive instruments, designed originally to listen for distant explosions, sometimes pick up the deep breathing of a wildfire far over the horizon. The signal is faint and slow, a quiet pulsing in the data, but it is there. Researchers are still learning how to read these signatures. One open question is whether the infrasound from a fire might one day warn distant towns that a violent fire vortex has formed, before the smoke even reaches them. Closer in, the sound changes. People who have survived fast-moving fires describe a kind of acoustic shadow just before the flames arrive, a strange muffling, as if the world has been wrapped in cloth. Birds go quiet, insects fall silent. Then the roar comes. Some scientists think the muffling is real, a result of hot, turbulent air bending sound waves and scattering them upward. Others think it is partly perception, the way fear narrows attention onto the larger noise approaching. The truth may be a blend of both. Inside the whirl itself, no one has ever stood and lived to describe the sound. What we have instead are recordings made by instruments placed near experimental burns, or by cameras left behind during evacuations. These recordings reveal something curious. The roar is not random. It has rhythm. Slow pulses, a few seconds apart, ride on top of the steady rush, as if the column is breathing. Researchers suspect these pulses come from the vortex itself, shedding small eddies, like a spinning top wobbling on its axis. But the exact mechanics, the why of that rhythm, remain incompletely understood. There are also the sounds the listener might not expect. The soft tinkling of glass as windows expand and crack from the heat, the metallic ping of expanding nails in old beams, the rush of water in nearby streams, suddenly amplified as the air above them grows hot and thin, the cracking of stones in a creek bed, breaking from temperature shock. Each of these is a small note in a much larger composition, and most of them happen at the edges of the fire, where life and stone meet flame. When the whirl finally collapses, the sound does not stop all at once. It fades in a strange, uneven way. The high snapping goes first, then the rushing hiss, then finally the deep rumble, which can linger for many minutes as residual heat keeps pushing air upward. Listeners often describe the silence afterward as heavier than ordinary silence, as if the air itself were tired. What the full acoustic fingerprint of a fire whirl really looks like, every frequency, every pulse, every hidden tone, is still being mapped. The roar is familiar to anyone who has heard one. Its deeper meaning, the message it carries about what is happening inside the column, is something the science is only beginning to learn. On a hot afternoon in May of 2003, in the small Australian community of Canberra, the sky began to do something fire scientists are still trying to fully understand. A wildfire that had been burning in the hills outside the city met a set of conditions that almost never line up. The air was bone dry, the ground was steep, the fuel was thick and ready, and somewhere in that mixture, the fire began to spin. What rose into the sky that day became the most carefully measured fire vortex in scientific history. The numbers it produced still feel almost impossible to hold in the mind. The column of rotating flame stretched nearly half a kilometer wide at its base. Some estimates placed its full height at over 5 kilometers into the atmosphere, inside that spinning shape. Wind speeds reached the rough equivalent of a strong tornado, somewhere between 200 and 250 kilometers per hour. The vortex tore the roofs from houses. It snapped mature trees at their trunks. It lifted heavy debris into the air and carried it across distances that defied easy belief. And it lasted not for seconds, as small fire whirls usually do, but for many long minutes. What makes the Canberra event so important to scientists is that it was the first time a fire vortex was given an official tornado rating by meteorologists. Until that day, fire whirls were treated as a kind of fire behavior. Afterward, researchers had to admit that a fire could, under the right conditions, produce a true tornado in every meaningful sense. The boundary between weather and combustion blurred in a way that the old categories could not quite hold. The mathematics of how such a thing forms remain only partly understood. Researchers know that rotation in the lower atmosphere can be stretched and tightened by a powerful updraft, much the way a spinning skater pulls in her arms and spins faster. A hot fire provides that updraft. The hotter the fire, the stronger the lift. The stronger the lift, the more sharply any existing spin in the air gets pulled into a tight, fast column. The equations describing this process are elegant. They use ratios of heat output to ambient wind, of column height to base width, of buoyancy to shear. On paper, the numbers behave nicely. In the real world, they often do not. Fires that should produce great vortices sometimes produce none. Fires that should remain calm sometimes throw out spinning columns no one predicted. The gap between the clean math and the messy fire is where much of the open question still lives. Heat output is one of the values scientists try to measure. A large wildfire can release energy at a rate that rivals the output of a small power plant. Some of the most extreme blazes have been estimated to release energy comparable to a steady stream of large bombs detonating every minute. These numbers are not used to frighten. They are used because they help explain why such a fire can punch a column of hot air so high that it touches the cold upper atmosphere and forms its own thundercloud above the flames. That cloud has a name. It is called a pyrocumulonimbus, a fire-borne storm cloud. The tallest examples have been measured at over 15 kilometers in height, taller than the cruising altitude of most passenger jets. From the ground, they look like a slow, grey-white anvil sitting above a smudge of smoke. From space, satellites have tracked them spreading their tops across hundreds of kilometers. Inside them, lightning can form. That lightning can start new fires, far ahead of the original blaze. The ratios involved in this scaling are part of what fascinates researchers. A modest doubling in fuel dryness can lead to a fourfold increase in flame intensity. A small change in wind shear, the way wind speed varies with height, can decide whether a vortex stays small and brief or grows into something that lasts. The math is sensitive in ways that make prediction extremely hard. Tiny inputs, large outputs, and so the Canberra vortex remains the benchmark, the case study returned to again and again. Its measurements are studied not because it was the biggest fire ever, but because it was caught in such detail. It revealed that the upper limits of fire vortex behavior are higher than scientists once believed. It also revealed how much remains hidden. The numbers describe what happened. They do not yet fully explain why that particular fire, on that particular afternoon, crossed the threshold that so many others never reach. The elegant mathematics points toward an answer that still slips just out of view. Fire seems simple at first. You need fuel, You need air. You need a spark. Bring those three things together, and a flame will follow. Yet anyone who has spent time studying wildfires knows that simplicity is a kind of illusion. The same flame that warms a hearth can, under the right conditions, rise into a spinning tower hundreds of feet tall. The difference between those two outcomes is razor thin, and it is in that thinness, that fragile balance, where so much of the mystery lives. Think of all the things that must align. The fuel must be dry, but not too dry. The wind must blow, but at a certain speed and from a certain angle. The land must rise and fall in a shape that channels the air just so. The sun must heat the ground unevenly. The humidity must drop into a narrow window. Change one of these variables, even slightly, and the fire behaves differently. A column may form, or it may not. A vortex may grow tall and slender, or it may collapse into smoke before anyone notices. This is why fire scientists speak with such humility. They can model many of the pieces. They know the broad rules. Heat rises, cooler air rushes in to replace it. Spinning columns form when horizontal wind shear tilts upward into a rising plume. These principles are well understood. The trouble is that the principles alone do not predict the outcome of any particular fire. Two fires burning side by side in what looks like the same forest, on what looks like the same afternoon, can do entirely different things. One stays low and creeps, the other rears up and starts spinning. The reasons remain only partly known. Some researchers think the missing piece lies in the fine structure of the air just above the flames. Tiny eddies, too small to measure with current instruments, may be the seeds that grow into the great whirls. Others suspect the answer lies in the fuel itself, in the way moisture is distributed inside leaves and branches at the moment of ignition. A third group looks to the terrain, arguing that subtle dips and ridges, smaller than a person can easily see, shape the air enough to tip the balance. Each theory has supporters. Each has gaps. The truth may involve all three working together in ways we have not yet untangled. What makes this delicacy more striking is how rare the dramatic events actually are. Most fires never spin at all. They burn, they spread, they smolder, they die. The whirls and the towering pyroconvective storms are the exceptions, not the rule. The Earth offers all the ingredients constantly. Yet most days nothing extraordinary happens. The fragile balance usually fails to align. It is only on certain afternoons, in certain valleys, under certain skies, that the conditions stack up just so. And then, briefly, the air itself seems to remember how to spin. There is something quietly humbling in this. The same planet that gave rise to forests and grasslands also gave rise, in those same forests and grasslands, to flames that can build their own weather. The thin layer of breathable atmosphere that lets us live also feeds the columns that rise into thunderclouds of smoke. The narrow band of temperatures that allows water and wood and life all to exist together is the same band that allows combustion to behave in surprising ways. If the atmosphere were thicker, fires would burn differently. If the air were drier or wetter, on average, the whirls might be more common, or might never form at all. The same balance that makes the world livable also makes the fire mystery possible. Some fire researchers have begun to suspect that we may never reach a complete theory of fire behavior, not because the science is impossible, but because the system is what scientists call sensitive to initial conditions. A tiny difference at the start of a fire can grow into a huge difference in how it ends. This is the same property that makes long-range weather forecasting so difficult. Fire, it seems, may belong to that same family of phenomena, deeply lawful at its core, yet practically unpredictable in its details. Others disagree. They believe that better sensors, finer models, and faster computers will eventually close the gap. The question is open. The debate is gentle but real. And in the meantime, the flames continue to do what they have always done, which is to surprise the people watching them. The fragile balance holds, and then it tips, and then it holds again. We are still learning, slowly, what determines the tipping. So we have come a long way together tonight, through marsh lights and ancient pillars, through firestorms and quiet blue flames. And here, in this slow stretch of the evening, it feels right to pause and look honestly at what we know, and at what still slips through the fingers of even the most patient scientists. Because the truth is, after centuries of careful watching, fire still keeps secrets. We know, in broad strokes, how a fire whirl forms. We understand that heat rises, that air rushes in to fill the space left behind, that small spins in the wind can be stretched and tightened by a strong updraft. We have equations that describe rotating fluids. We have wind tunnels and burn chambers and high-speed cameras. We have satellites that watch wildfires from far above, tracking their plumes hour by hour. And yet, when a real fire begins to spin out on a hillside, scientists often cannot say why this fire, in this place, at this moment, has chosen to turn. That gap between the lab and the open world is one of the great unsolved spaces in fire science. In a controlled room, with steady fuel and shaped vents, researchers can summon a whirl on command. They can measure its height, its rotation, its temperature. They can even coax it into that strange blue form, burning clean and quiet. But the moment you step outside, into rough ground and shifting winds and tangled fuels, the rules grow slippery. Two fires that look almost identical can behave in completely different ways. One stays calm. The other suddenly stands up and spins. One open question is how small motions in the air become large ones. A wildfire is full of tiny eddies, little curls of wind no bigger than a person. Most of them die quickly. A few somehow gather strength and grow into towers. Researchers wonder what tips the balance. Some think it comes down to the steepness of the temperature difference between the flame and the air around it. Others suspect that the shape of the land matters far more than we realize, that hidden bowls and ridges act like invisible funnels. Both ideas have evidence. Neither tells the whole story. There is also the puzzle of when a fire crosses from being a fire into being a kind of storm. We can see it happen in satellite images. A plume rises, swells, flattens into an anvil, and begins to throw lightning. But the exact threshold remains unclear. Why does one fire on a hot afternoon stay a fire, while another, in seemingly similar conditions, builds a thunderhead 5 miles tall? Some researchers point to the moisture in the fuel itself, the water released as plants burn. Others point to the moisture already waiting in the upper air. The honest answer is that we are still learning to read these signs. Prediction is another quiet frontier. Fire behavior models have grown more powerful each decade. They can guess at spread rates, at flame heights, at the general direction a fire will travel. But the sudden, violent behaviors, the whirls, the blow-ups, the fires that seem to leap against the wind, still catch forecasters off guard. There is no reliable way, yet, to look at a landscape in the morning and say with certainty that a fire whirl will form there by evening. The variables are too many. The interactions are too tangled. Even the chemistry holds surprises. The blue fire whirl, that small clean vortex first noted only a handful of years ago, hinted that flames can organize themselves in ways no one expected. Researchers are still working out What other forms of combustion might be hiding in plain sight, waiting for the right conditions to appear? Some wonder if there are stable flame shapes we have simply never seen, because the precise mix of fuel and air and spin has never quite lined up in front of a careful observer. And then there are the old reports, the ones that do not fit easily into any current theory. Flames in calm air, glows over wet ground, lights that drift slowly and then wink out. Some of these almost certainly have ordinary explanations we have not yet identified. Others may turn out to be tricks of memory and weather. A few, perhaps, point to something genuinely new. What is lovely about all of this is that the gaps are not failures. They are invitations. Every unanswered question is a place where a patient mind, years from now, might find a small new piece of understanding. Fire has been with us since before we were fully human, and still it has more to teach. We do not know everything. We are not even close. And tonight, that feels like a comfort rather than a worry. In quiet laboratories around the world, small fires are still being made on purpose. They are lit inside metal chambers and glass tubes on round turntables that spin slowly under careful light. Researchers stand at a distance, watching how the flames lean, twist, and pull themselves upward. Each test is a small question asked again and again, in the hope that the flames will give back a small piece of an answer. Some of these laboratories use thin sheets of fuel poured into shallow pans. The pan sits in a slotted enclosure where air can enter from the sides at carefully chosen angles. When the air comes in just right, the flame begins to spin on its own. The scientists do not push it. They only set the stage, and the fire finds its own shape. From this simple test, much of what we know about fire whirls has been learned, and much that we still do not know has been revealed. One ongoing question is why a fire whirl, once formed, often burns far hotter and brighter than the same fuel burning in open air. Some researchers think the spinning column pulls oxygen inward in a tighter, more efficient stream. Others think the rotation stretches the flame into a thinner sheet, where the fuel and air can mix more completely. Both ideas may be partly true. Both may be missing a piece. The small flames in the chambers still surprise the people who watch them. The blue fire whirl is one of the strangest of these surprises. It was first made by accident, in a tank of water with a layer of liquid fuel floating on top. A normal yellow whirl formed, then collapsed into a small, quiet blue cone that burned with almost no soot. The cone was no taller than a hand, and it gave off a soft hush rather than a roar. Researchers are still studying why it forms, what holds it together, and whether the same chemistry could one day help clean up oil spills with less smoke. The answers are not yet settled. Other laboratories use computers instead of flames. They build models of swirling air and burning fuel, with millions of tiny boxes stacked together, each one solving small equations about heat and motion. The models can show whirls forming on a screen, twisting and breaking apart in slow motion. They are useful, but they are not perfect. The real fires in the real world still do things the models do not predict. A flame will lean away it should not lean. A whirl will form where the math says it should not. The gap between the screen and the field is the gap the researchers are trying to close. There are also field experiments, done on calm days in open clearings. With permission and careful watch, small piles of brush are lit in patterns that have been used before, and instruments measure the wind, the heat, and the rise of the column. Cameras film the flames from every side. Sometimes a whirl appears, sometimes it does not. The conditions that seem identical on one afternoon produce nothing on the next. This stubborn unpredictability is itself a clue, though no one is sure yet what it means. Looking forward, the questions grow larger rather than smaller. As the climate shifts, fires in many parts of the world are burning hotter, longer, and in places they did not burn before. Some researchers wonder whether large fire whirls and pyroconvective storms will become more common in the coming decades. Others think the changes will be more uneven, with some regions seeing more extreme fire weather and others seeing less. The forecast itself is an open question, made of many smaller open questions stacked on top of each other. In 1,000,000 years, the forests we know will be gone, replaced by other forests, or by grasslands, or by deserts, or by ice. New fuels will burn in new ways. The basic physics of spinning flame will still be the same, governed by the same simple rules of air and heat. But the shape of fire on this planet will keep changing, as it has changed across every age before us. In 1,000,000,000 years, the sun itself will burn hotter, and the surface of the earth may not hold flame as it does now. Even then, somewhere, something will still spin in the heat. The pattern is older than the planet. For now, the laboratories stay quiet. Small flames rise and turn and fall. Notebooks fill with numbers. The questions outlast the answers, and that may be the most honest thing anyone can say about fire. Now we step back. We step very far back, until the fire whirl is just a small bright spiral on the surface of a quiet blue planet. And the planet is just one warm stone, turning slowly in a thin shell of air. From this distance, the flame becomes something simpler. It is heat finding its way upward. It is matter rearranging itself, giving off light and warmth as it changes shape. The same thing has been happening in this universe for a very long time, in many different forms, on many different worlds. The atoms inside the flame are old. The carbon in a burning branch was once locked inside the leaves of a tree. Before that, it floated in the air as a gas. And before that, deeper in time than the mind can easily hold, those carbon atoms were forged inside the hearts of stars. Every fire on Earth is, in a quiet way, starlight being released again. The oxygen feeding the flame has its own long story. It was breathed out by tiny green cells in the ocean billions of years ago, when the world was still young and the sky still dim. Those little cells changed the whole sky. They filled it with the gas that now feeds every fire, every breath, every spinning column of flame on every dry hillside. So when a fire whirl rises from a burning forest, it is, in some sense, a meeting of ancient things. Sunlight stored inside wood, oxygen released by long-dead ocean life, heat lifting upward through air shaped by the spin of the planet itself. The whirl is brief, but the pieces that make it are very, very old. This is part of why the mystery feels so deep. A fire whirl is not just a strange weather event. It is a small window into how energy moves through the world. It shows how a flat sheet of heat can suddenly choose to spin. It shows how the same physics that turns hurricanes also turns flame. The big patterns and the small patterns share the same quiet rules. Scientists who study fire whirls often speak of them with a kind of soft respect. They know the basic ingredients. They know that heat rises, that spin gathers, that vortices stretch and grow. And yet, when they try to predict exactly when a whirl will appear, exactly how tall it will grow, exactly which direction it will lean, the answers blur. The fire seems to hold a few of its secrets back. Maybe that is fitting. We are, after all, looking at one of the oldest forces our species has ever known. Long before written language, long before farming, long before villages, our ancestors sat around fires at night. They watched flames flicker and twist. They saw sparks rise into the dark like tiny stars. They wondered. They told stories. And on rare nights, perhaps, they saw a small fire devil dance away from the embers and vanish into the grass. We are still those same watchers. The tools have changed. We have cameras now, and computer models, and laboratory burners that can spin blue flame in a glass column. But the wonder is the same wonder. The question at its heart has not really changed. What is this thing we have lit? What is it doing? Why does it sometimes leap up and spin? The embers may one day reveal more. Future scientists with better sensors and faster models may finally describe a fire whirl from its first breath to its final fade. They may learn to predict which wildfires will spawn their own storms and which will burn out quietly. They may even find new kinds of flame we have not yet seen, hidden inside fuels we have not yet tested. Or they may find that some part of the mystery stays open, that the fire, like the weather, like the ocean, like the deep slow turning of the earth, keeps a piece of itself just out of reach. There is no shame in that. A world without any mystery left would be a smaller world to live in. For tonight, the embers are enough. The slow red glow of a dying fire, the thin curl of smoke rising into still air, the faint warmth on the skin, the old story of starlight returning, in a different form, to the night sky. You are made of the same atoms as the flame, the same calcium, the same carbon, the same iron, all once cooked inside ancient stars and scattered across the dark. You are, in your own quiet way, a slow and gentle fire, burning softly, glowing warmly, wondering as you drift about all the other fires of the world. And so we come to the quiet end of our long, slow look at flame. The fires we wondered about together can rest now. The whirling columns, the soft blue lanterns over the marsh, the eternal flames burning on hillsides for thousands of years, the great rotating storms born from forests in summer. Let them all settle. Let the embers cool in your mind. There is nothing left to chase tonight. Picture the earth from a great calm distance, a blue and white sphere, turning slowly in the dark. Half of it lit by soft sun, half of it wrapped in night. From that distance, fire is only a faint warm pinprick here and there, a candle in a window, a small fire in a stone ring, a lantern carried along a path. The wild burning we spoke of becomes only a quiet glow against a vast and gentle world. The planet has been doing this for a very long time, spinning, cooling and warming, letting weather move across its skin like soft brushstrokes. Long before any of us were here, fire was already finding its strange shapes in the wind. The first spinning column of flame happened with no one watching. It rose, it turned, it faded back into the air. The earth did not need an audience. It only needed fuel and heat and a small twist of moving air. That is a calming thought in its own way. The mysteries we explored tonight will keep being mysteries whether or not anyone is awake to notice. The blue fire whirl will form again in some quiet laboratory, glowing like a small jewel above a pool of fuel, somewhere on a peat bog tonight. A soft pale light may drift just above the wet ground. Somewhere a coal seam deep below a hillside is glowing red without any flame, patient and slow, the way it has been for centuries. The world keeps its own quiet rhythms while we sleep. Let your breathing slow with that rhythm, in and out, the way a tide comes in and goes out, the way a flame rises and settles, the way a planet turns its face toward the sun and then away again. You are a small, warm creature on a soft, turning world, and there is nothing you need to solve tonight. The scientists in their labs will keep working. The forests will keep growing. The oceans will keep rocking under the moon. None of it asks anything of you right now. Picture, if you like, a wide, dark ocean under a low moon. The water is calm. Small, silver ripples move across the surface. Far off, a single lighthouse turns its slow beam, sweeping the dark, sweeping back. That is all. No fire, no storm, just the soft breath of the sea and the steady turning of a quiet light. Or picture a meadow at the very end of a summer day. The grass is long and bending in a low breeze. The sky has gone the color of soft peach and lavender. Somewhere far away, a single bird calls once and then is silent. The day is letting go. The night is settling in. The earth has done its long work, and now it rests. We do not know everything. We will probably never know everything. The flames will keep showing us new shapes. The fire whirls will keep surprising the people who study them. The blue fire whirl will keep its secrets a little longer. The eternal flames on the hillsides will keep burning, slow and patient, while the questions around them sharpen and soften and sharpen again. That is a good thing. A world without mysteries would be a smaller world. For tonight, you do not have to hold any of it. You can set it gently down, the way you might set down a warm cup at the end of a long evening. The wandering will still be here in the morning if you want to come back to it. The flames will still be dancing in some quiet corner of the planet. The earth will still be turning, soft and steady beneath you. Rest now. Let your shoulders soften. Let your hands grow heavy. Let your thoughts drift the way smoke drifts, slow and shapeless, into the dark. The fires we spoke of are far away. You are warm. You are safe. The night is wide and kind. The planet is holding you the way it has held every sleeping creature for a very, very long time. May your dreams be gentle and slow. May they wander through soft places. May they ask easy questions and find no need for answers. Subscribe for a brand new Earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.